Hi. Today we're going to find out a general formula for the integral from minus infinity to infinity of sine n of x over x to the n dx for n even and n greater than or equal to 2. And for these n, this is a convergent integral, as is easily seen. And we're going to call this will be our target integral. We're going to call it I of n. A known formula for the nth power of sine of x is minus 1 to the n over 2 divided by 2 to the n minus 1 times the sum as k goes from 0 to n over 2 minus 1 of minus 1 to the k and choose k cosine of n minus 2k times x plus 1 over 2 to the n times n choose n over 2. And you notice there are no powers of cosine here. And to do this, to find this formula, we're going to use a residue theory from complex analysis. So in that regard, let's let f of z equal e to the I n minus 2k times z all over z to the n. And furthermore, let's let g of z equal minus 1 to the n over 2 over 2 to the n minus 1 times the sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k f of z plus 1 over 2 to the n choose n over 2 times 1 over z to the n. Now, if you look closely, you'll notice that sine n of x over x to the n is simply the real part of g of x for x, a real number. Right here, if we plug in a real number x, f of z, or f of x rather, will be e to the I n minus 2k times x over x to the n. And of course, this breaks down into a cosine of n minus 2kx plus I sine of n minus 2kx over x to the n. And the real part will be our formula here for sine n of x over x to the n. And this will be our integration path here. It's a typical integration path. We're going to start, maybe we can say we're going to start from minus capital R to minus epsilon on the real axis. Then we're going to do a semicircle that goes down to minus epsilon I and back up to epsilon. And from there, we'll go from epsilon to capital R along the x-axis. And then we're going to do a big semicircle going from capital R to minus R. And we're going to call this big arc capital gamma, and this little arc down here, we'll call that little gamma. And furthermore, we notice that g of z has one pole, and it is a pole of order n at z equals 0. Right here, it's part of f of z, and it's also comes over here in this last term. Okay, here are a couple of initial observations we should make. Number one, the integral from minus r to minus epsilon of the imaginary part of g of x dx plus the integral from epsilon to r of the imaginary part of g of x dx equals 0. Well, why is that? How can we say that? Well, the imaginary part of g of x is an odd function, and we have symmetric integration here on either side of 0. And this fact implies our second observation, and that is the limit as epsilon goes to 0 and as r goes to infinity of the integral from minus r to minus epsilon g of x dx plus the integral from epsilon to r of g of x dx equals the integral from minus infinity to infinity sine n of x over x to the n dx, which is equal to I of n, our target integral. Okay, continuing on, by Jordan's lemma, we have the limit as r goes to infinity of the integral over capital gamma of f of z dz equals 0. And Jordan's lemma is a famous result, and you can find that in any complex analysis book if you like. And it is also clear that the limit as r goes to infinity of the integral over capital gamma of 1 over z to the n dz is also 0. So therefore, the limit as r goes to infinity of the integral over capital gamma of g of z dz is equal to 0. Now, let's turn our attention to the integral over small gamma. Now, this is much harder. So we have the little semicircle here. And we're going to parameterize that with a theta. So we're going to let z equals epsilon e to the I theta, as theta goes from minus pi to 0. Well, then dz will be equal to I epsilon e to the I theta d theta. So the integral over small gamma f of z dz will equal the integral from minus pi to 0 of e to the I n minus 2k epsilon e to the I theta, that's all in the exponent here of e, divided by epsilon to the n e to the I theta n times I epsilon e to the I theta d theta. Well, now we're going to change this e to the I n minus 2k epsilon e to the I theta in a Taylor series of e to the something. Of course, that's a well-known series. So this whole thing equals the integral from minus pi to 0. Now, times the sum as j goes from 0 to infinity of I to the j n minus 2k to the j epsilon to the j e to the I theta j over j factorial. That is just this numerator right here. Keep in mind, I didn't write it very well, but this whole thing here is in the exponent of e. Okay, that times I over epsilon to the n minus 1 e to the I theta n minus 1 d theta. Okay, we're going to pull out an I over epsilon to the n minus 1. And we're going to break this j sum here into two parts. First part will be from j to 0 to n minus 1 of, again, I to the j n minus 2k to the j epsilon to the j e to the I theta j over j factorial, plus the rest of that series from j equals n to infinity. All of that, again, times e to the minus I theta n minus 1. I'm just bringing this into the numerator here. Okay. Well, this equals I over epsilon to the n minus 1 times the quantity, our first term. Our first term has a finite sum here, so we can switch the summation and integration without having to worry about anything. So we have the sum as j goes from 0 to n minus 1 of I to the j n minus 2k to the j epsilon to the j over j factorial times the integral from minus pi to 0 of e to the I theta j minus n plus 1 d theta. Now, plus the second term up here. We're going to leave the order of the integration summation the same as it was up here. So the integral of minus pi to 0. The sum as j goes from n to infinity of the same stuff, I to the j, n minus 2k to the j, epsilon to the j over j factorial, e to the I theta, j minus n plus 1 d theta. And we're going to call the integrand of the second term s. So this part right here that I'm circling with the arrow, the integrand, we're going to call that capital S. Okay, continuing. Let's let epsilon for now be less than 1. Of course, eventually we want to bring epsilon down to 0. Of course, epsilon is greater than 0. I should have maybe written that. And referring to S again, right here, the absolute value of S is going to be less than or equal to the sum as j goes from n to infinity of the absolute value of everything on the inside here, all of that. Okay, when we take individual absolute values here, the I to the j and the e to the I theta to the j minus n plus 1, those are both going to be 1. And everything else is always positive. So this is going to equal the sum as j goes from n to infinity of n minus 2k to the j, epsilon to the j over j factorial. And we're going to pull out an epsilon to the n. Every term has at least an epsilon to the n. And then anything j greater than n, that's going to be a smaller. It'll be a smaller amount because epsilon is less than 1. So this will be less than epsilon to the n, the sum as j goes from n to infinity, of n minus 2k to the j over j factorial, which is less than epsilon to the n of the sum over j from 0 to infinity of n minus 2k to the j over j factorial. And of course, this equals epsilon n e to the n minus 2k. Therefore, the absolute value of I over epsilon to the n minus 1 times the integral from minus pi to 0 of s d theta is less than or equal to 1 over epsilon to the n minus 1. The absolute value of I is 1, times the integral from minus pi to 0 of absolute s d theta. And of course, we determine that absolute s is less than this amount here, epsilon n e to the n minus 2k. So this whole thing is less than epsilon to the n e to the n minus 2k over epsilon to the n minus 1. And when we do the integration, we get a pi. This will just be a constant in here. And we're integrating from minus pi to 0. Excuse me. And this equals epsilon e to the n minus 2k times pi. And, of course, as epsilon goes to 0, this quantity will also go to 0. Therefore, we can say the limit as epsilon goes to 0 of the integral of over small gamma of f of z dz equals simply the limit as epsilon goes to 0 of our first term back here. This part will go to 0. This is what's going to be left over. And I have written that again right here. This is simply the first term of our integration here. Okay. Well, doing the integration, well, first we're going to break this sum. It says here j to 0 to n minus 1. We're going to go from j 0 to n minus 2 and then tack on the n minus 1 term. Why do we do that? Because they're going to have different antiderivatives. Because at the n minus 1 term, this exponent here is 0, which will turn this integrand into 1. So doing that, we're going to have the limit as epsilon goes to 0 of I over epsilon to the n minus 1, the sum now j from 0 to n minus 2 of the usual stuff, I to the j, n minus 2, k to the j, epsilon to the j over j factorial. Now our antiderivative then, e to the I theta, j minus n plus 1 over I, j minus n plus 1 from minus pi to 0. Then plus our n minus 1 term, I over epsilon to the n minus 1, I to the n minus 1, n minus 2k to the n minus 1 over n minus 1 factorial, epsilon to the n minus 1 times theta, because we're integrating 1. And this goes also from minus pi to 0. Okay, doing that, putting those limits in, we get the limit as epsilon goes to 0 of 1 over epsilon to the n minus 1 times the sum as j goes from 0 to n minus 2 of the usual stuff, I to the j, n minus 2k to the j, epsilon to the j over j factorial. Now, times the quantity 1 minus 1 to the j minus n plus 1 over j minus n plus 1 plus, now the n minus 1 term, I to the n, n minus 2k to the n minus 1 over n minus 1 factorial times pi. And let's note quickly that 1 minus 1 to the j minus n plus 1 will equal 0 when j is odd, and it'll equal 2 when j is even. And that is because n is even. Okay, let's now compute the integral around small gamma of 1 over z to the n dz. We're going to need that as the last term of our g of z. And using the same substitution for z that we did before, this will equal the integral from minus pi to 0 of I epsilon e to the I theta over epsilon to the n e to the I theta and d theta, which equals I over epsilon to the n minus 1, the integral from minus pi to 0 of e to the I theta 1 minus n d theta. Now this equals I over epsilon to the n minus 1, e to the I theta times 1 minus n over I times 1 minus n, simply our antiderivative from minus pi to 0. And calculating that, this is equal to 1 over epsilon to the n minus 1 times 1 minus n times our quantity again of 1 minus 1 to the n minus 1. Now this will equal 2 over 1 minus n epsilon to the n minus 1. And that is because n is even. So n minus 1 is odd, so you get 1 minus a negative 1, and that equals 2. Okay, bringing these last two results together will yield what? We have this result here, and we have this result here. Plugging these into our g of z will yield the limit as epsilon goes to 0 of the integral over small gamma of g of z dz will equal the limit as epsilon goes to 0 of the entire quantity, just plugging these things in, of minus 1 to the n over 2 to the n minus 1. The sum as k goes from 0 to n over 2 minus 1 of n choose k times minus 1 to the k times the quantity 2 over epsilon to the n minus 1 times the sum as j goes from 0 to n minus 2, where j is just even. Remember, we eliminated the j odd terms because they were 0. Of the usual stuff, I to the j, n minus 2k to the j, epsilon to the j over j factorial, j minus n plus 1, plus, this is our n minus 1 term again, I to the n minus 2k to the n minus 1 over n minus 1 factorial times pi, plus our last term from g to z, 1 over 2n, 2 to the n rather, times n choose n over 2 times 2 over 1 minus n epsilon to the n minus 1. This here is just bringing down this and inserting it into our g of z. And this right here is just what we calculated here, and also inserting it into our g of z. Okay, now this is quite intimidating actually, but we're going to pick it apart a little bit at a time. Notice we have all these epsilons in the denominator, and oh no, what's going to happen when we take epsilon to 0? It's going to blow up. Well, it's actually not going to blow up. We're going to find out why. So let's focus on the terms involving an epsilon. The first term we're going to look at is the 1 over epsilon to the n minus 1 term, the largest exponent of epsilon term. Where does that come from? Well, that'll come from, one of the parts will come from the j equals 0 term up here, because we'll have e to the 0 over, or I'm sorry, epsilon to the 0 over epsilon to the n minus 1. And the other epsilon to the n minus 1 term comes from our second term here. So let's bring that down. So the 1 over epsilon to the n minus 1 term will be minus 1 to the n over 2 over 2 to the n minus 1 times the sum as k goes from 0 to n over 2 minus 1, n choose k minus 1 to the k times 2 over 1 minus n, plus 1 over 2 to the n choose n over 2 times 2 over 1 minus n, times, of course, 1 over epsilon to the n minus 1. Just plugging in j equals 0 here and bringing down this term as well. And we're going to define this as capital T sub n minus 1 times 1 over epsilon to the n minus 1. So what I'm saying is, what I'm calling capital T sub n minus 1 is just this stuff here in parentheses, just so I can refer to it easily later on. All right, to continue, we're going to need the following combinatorial result from Table of Integrals, Series, and Products by Gratschetein and Reischek. Anyway, the result we're going to need, I'm going to call it number 1, says the sum as k goes from 0 to capital N of minus 1 to the k, n choose k equals minus 1 to the capital N, little n minus 1 choose capital N. This is for little n greater than or equal to 1. Now, t sub n minus 1, I think we'll just rewrite it here, equals minus 1 to the n over 2 to the n minus 1. The sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k, 2 over n minus 1, plus 2 over 2 to the n, 1 over n minus 1, n choose n over 2. All right, let's pull some of the stuff out of here. This equals 2 times minus 1 to the n over 2 to the n minus 1 times n minus 1 times the sum as k goes from 0 to n over 2 minus 1 of n choose k times minus 1 to the k plus 2 over 2 to the n, 1 over n minus 1, and choose n over 2. Okay, now using equation 1 here, or result number 1 from our book, this will equal, putting that into the first term, 2 times minus 1 to the n over 2 to the n minus 1, n minus 1, times minus 1 to the n over 2 minus 1, times n minus 1, choose n over 2 minus 1. Just plugging in here, n over 2 minus 1 going into capital N. That's all we did there. Plus the second term again, 2 over 2 to the n, 1 over n minus 1, and choose n over 2. Okay, let's pull out some common factors. This will equal 2 over 2 to the n, n minus 1, times the quantity now, 2 times minus 1 to the n over 2, minus 1 to the n over 2 minus 1, times n minus 1, choose n over 2 minus 1, plus n choose n over 2. Now you'll notice we have a minus 1 to the n over 2 times a minus 1 to the n over 2. Well, that's just minus 1 to the n, which is 1 since n is even. And we still have a minus 1 to the minus 1 left over. So this thing will equal 2 over 2 to the n, n minus 1, times the quantity minus 2 times, putting all that out in large form, would be n minus 1 factorial over n over 2 minus 1 factorial, times n minus n over 2 factorial by the definition of this symbol here. And now we're going to multiply by n over n and n over 2 over n over 2, simply multiplying by 1, plus our last term, n choose n over 2. Well, bringing this n together with this will create an n factorial, and bringing this n over 2 in the bottom here, combining with this, n minus 2 minus 1 factorial, will bring us a n over 2 factorial. And then what's left over will be a n over 2 over n, which is simply a 1/2. And so we get down here, this whole thing will equal 2 over 2 to the n, n minus 1, times the quantity minus 2, and choose n over 2 times our 1/2, plus n choose n over 2. Of course, combining those two terms will equal 0. Therefore, we have shown that in actuality, there is no 1 over epsilon to the n minus 1 term. Simply because we have shown that t sub n minus 1 is 0. Okay, let's continue. All right, now let's calculate the other 1 over epsilon to the m terms. You'll notice here we have an epsilon to the j over epsilon to the n minus 1. Well, that equals epsilon to the j minus n plus 1. So if we set minus m equal to this j minus n plus 1, this implies that j equals n minus m minus 1. And since j and n are even, m must be odd. Therefore, 1 is less than or equal to m is less than or equal to n minus 3, where m is odd. And this m will be our exponent of epsilon in the denominator. Okay, from the same source as from above, we also have the result, we're going to call it number 2 in our literature, which says sum as k goes from 0 to n of minus 1 to the k, and choose k, times the quantity alpha plus beta k all to the s equals 0. And this is valid for n is greater than or equal to s plus 1. This comes from the same source here, the table of integrals, series, and products, if you want to check that out. Okay, let's look at the 1 over epsilon to the m term. Okay, plugging in, to find this term, plugging in j equals n minus m minus 1 into here, that'll give us 2 times minus 1 to the n over 2 times I to the n minus m minus 1 over epsilon to the m, 2 to the n minus 1, n minus m minus 1 factorial times minus m times the sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k n minus 2k to the n minus m minus 1. And we're going to define this again as capital T sub m times 1 over epsilon to the m. And this time I'm going to call this sum here that I'm outlining, I'm going to call that capital T, so I can refer to it easily later on. Okay, this term here is simply plugging in our j at n minus m minus 1 into our result here. Right there. So that's where the only epsilon to the m terms will occur, is in that first term. Okay. We notice that our t, capital T, sums from k equals 0 to n over 2 minus 1. But I was wondering, what would be the sum as k goes from n over 2 plus 1 all the way to n? In hopes of maybe combining these two later on and adding an n over 2 term to get a full sum as k goes from 0 to n. Well, let's write that up. So the sum as k goes from n over 2 plus 1 to n of n choose k minus 1 to the k, n minus 2k to the n minus m minus 1. All right, well, let's re-index. Let's change k to n minus k. And that brings us to the sum as k goes from 0 to n over 2 minus 1 of n choose n minus k minus 1 to the n minus k times the quantity minus n plus 2k to the n minus m minus 1. Okay, notice this sort of reverses the order. When k equals 0 here, when k equals 0 here, it's the same as when k equals n up in this series, and so on. Just goes in opposite order. It goes in descending order instead of ascending order. All right, but anyway, simplifying, this equals the sum as k goes from 0 to n over 2 minus 1 of n choose k. Why is that? Well, n choose k is the same as n choose n minus k. Minus times minus 1 to the k, well, that's the same as minus 1 to the n minus k, since n is even. And it doesn't matter if it's a k or a minus k when it's the power of minus 1. Times n minus 2k to the n minus m minus 1. Well, why is that? Well, n minus m minus 1 is an even number, since n is even and m is odd. So we're just multiplying out the negative 1 here. And this as we can see, is the same as capital T now. All right. Therefore, if we wanted to know the sum as k goes from 0 to n of this stuff, n choose k minus 1 to the k times n minus 2k to the n minus m minus 1, well, that'll simply be 2 times our capital T plus the n over 2 term, which will be n choose n over 2 minus 1 to the n over 2 times 0 to the n minus m minus 1. Just plugging in n over 2 to this sum end here. Well, using our equation 2, recalling this right here, everything there is satisfied, and we get capital T must be equal to 0. Dividing by 2 here. This is 0. Okay. Well, therefore, we have shown that capital T sub m equals 0, which of course implies there is actuality no 1 over epsilon to the m term. For 1 is less than or equal to m is less than or equal to n minus 3. M is odd. And there are no m even terms. Okay. So far we have shown that T sub n minus 1 is 0 and T sub m is equal to 0. Therefore, those are the only 1 over epsilon terms at all. And therefore, we have shown all the terms involving epsilon don't exist. Therefore, this implies the limit as epsilon approaches 0 of the integral around small gamma of g of z dz equals the limit as epsilon approaches 0 of minus 1 to the n over 2 to the n minus 1 times the sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k I to the n minus 2k to the n minus 1 over n minus 1 factorial times pi. Why is that? Because we have shown all those are just 0 and all those are 0. This is the only thing left. This is the only term that does not have an epsilon in it. So it doesn't matter what epsilon is, letting epsilon approach 0 doesn't matter anymore. So this simply equals this amount, pi times 1 over 2 to the n minus 1 factorial times the sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k, n minus 2k to the n minus 1. And we can see that because I to the n here, you're wondering what happened to the I to the n? Well, I to the n is minus 1 to the n over 2. Combining with this minus 1 to the n over 2 brings us a minus 1 to the n, which is 1, because n is even. And you can see the rest of that just comes down. Okay, compiling the results so far. We have, from the beginning, if you will recall, on page 1, we will have the integral from minus infinity to infinity of sine n of x over x to the n dx plus the limit as epsilon approaches 0 of the integral around small gamma of g of z dz plus the limit as r approaches infinity of the integral around capital gamma of g of z dz equals the residue of g of z at 0 times 2 pi I according to our residue theory. Well, this first term is simply our I of n, our target integral that we want to solve for. The second term here is simply what we just calculated in the box. We'll bring that down right here. And we learned at the very beginning that this quantity is 0 due to Jordan's lemma and the fact that the integral around 1 over z to the n dz on gamma will approach 0. So this equals 2 pi I times the residue of g of z at 0, which equals, of course, 2 pi I times 1 over n minus 1 factorial, the n minus first derivative of z to the n times g of z, calculated at z approaching 0. Okay, we're almost there. Let's take it the rest of the way. Well, z to the n g of z equals minus 1 to the n over 2 to the n minus 1 times the sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k e to the I times n minus 2k times z plus 1 over 2 to the n times n choose n over 2. Just multiplying z to the n times g of z. Taking the n minus first derivative of that brings us to minus 1 to the n over 2 to the n minus 1 times the sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k I to the n minus 1, n minus 2k to the n minus 1 times e to the I n minus 2k z. Just differentiating this exponential n minus 1 times. And this equals 1 over I times 2 to the n minus 1 times the sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k n minus 2k to the n minus 1 at z equals 0. We simply plug in z equals 0 right here. Okay, well, finally, this implies I to the n equals, just solving for I to the n here, so we bring this to the other side, equals 2 pi I over n minus 1 factorial times 1 over I 2 to the n minus 1 times this very familiar sum now, minus pi over 2 to the n minus 1 factorial times this same sum. Well, these i's are going to cancel, and what's left is we got 2 of these things minus 1 of these things will equal just 1 of these things, which will be pi over 2 to the n minus 1 factorial times the sum as k goes from 0 to n over 2 minus 1 of n choose k minus 1 to the k times n minus 2k to the n minus 1. And this is valid for n is even and n is greater than or equal to 2, of course. And here ends the video. Thank you for watching.